right, we have finished our discussion on polynomial functions. And so we're going to go ahead and switch gears, and we're going to look at a couple of other things. In this particular section, we're going to talk about rational functions. Now, rational functions are things that we have talked about in previous courses, but we haven't really done a whole lot with them. We've mostly just solved rational functions or evaluated rational functions. We are actually now going to talk about graphing rational functions. So to start us off with, let's talk about what is a rational function. A rational function is a function f of x that is equal to p of x over q of x, where both of these are polynomial functions. We also have the additional requirement that q of x cannot equal 0. So if we divide two polynomials, we're looking at a rational function. Now, in terms of graphing rational functions do all sorts of crazy things, which is why we haven't talked about it until now. And so there's a lot that we're going to be looking at, but the main thing that I do want to point out is we are just going to be extending the concepts that we have looked at in previous sections and classes. So the first thing that we have is we have domain of rational functions. So far in this course, we've talked about linear, we've talked about quadratic, and we've talked about polynomial functions. And one of the main things about those three types of functions is that they have a domain of all real numbers. Rational functions, this is going to be the first type of function that we look at where we have trouble spots. The first thing to remember is a rational function is first and foremost a fraction, it's division, and there's one thing that we are not allowed to have in terms of fraction or division, and that is we're never allowed to divide by 0. We are never allowed to have a denominator of 0. Now, we've looked at this in previous courses, and so what we're going to do is to find the domain of a rational function. We want to set the denominator equal to 0 and solve. The domain of a rational function is all real numbers except where the denominator is equal to 0. We can denote this in two ways. The first way we can do is we can use the not equal to symbol. We can just say x is not equal to whatever. But we have introduced the union symbol in this class, and so the other way that we can write this is in interval notation using the union symbol. We're going to look at both of these notations as we progress. All right, so we're going to go ahead and start with some examples. And we are going to go ahead and talk about, one, is it rational? And two, for all of these, we want to state what is the domain. All right, our first example is example A. And so example A, the first thing is it rational? And so what we want to check for is the top. Is it a polynomial? It is. The bottom, is it a polynomial? It is. It's a linear equation. And remember, linear equations are polynomials. And so this is a rational function. All right, the next thing that we want to do is we want to find the domain. And so for our domain, what we're going to do is we're going to take the denominator. We're going to set it equal to 0, and we want to solve. So we're going to start by adding 5 to both sides. And then we're going to divide by 4. We get x equals 5 over 4. Now again, remember that we are trying to find the domain. And domain is what are all the x values we're allowed to plug in. Well, it's not going to be one answer. And so what we want to do is we're going to take this number. Remember, this is the number that makes the denominator equal 0. We are never allowed to have a denominator of 0. And so we're going to go ahead and just rewrite this with a not equal symbol. If you want, you can put this in set notation, and our set notation is going to look like this. And this is saying that x is a number, x is not equal to negative 5 over 4. If we want this in interval notation, on the other hand, well, basically we want to start with all of our all real numbers. And so all real numbers, remember, is negative infinity to infinity. But we want to get rid of 5 over 4. So what we're going to do is we're going to look at all the numbers on the left of 5 over 4. We cannot equal 5 over 4, and so we're going to put a parenthesis. And then we want all the numbers that are strictly larger than 5 over 4. And so we're going to put another parenthesis with 5 over 4 on that side. All right, that is example A. Let's go ahead and look at a couple more. All right, let's come over to example B. Example B, we have g of x equals the absolute value of x minus 1 over x plus 1. And so the first question we want to ask is it a rational function? This is not rational. Remember, in order to be rational, both the top and the bottom have to be polynomials. The numerator is not a polynomial. And so that means that this is not going to be a rational function. All right, the second thing that we want to do is we want to go ahead and determine the domain. All right, so for our domain, we are going to set the denominator equal to 0. And if we solve this, we get x equals 1. Again, we are talking about domain, and so we do want to go ahead and mark out the equal sign, and we're going to replace it with a not equal sign. So we get x is not equal to 1. You may go ahead and leave it like that. I'm perfectly fine with that. You don't have to add the squiggly brackets and everything else. All right, in interval notation, again, we're going to do the same thing. We're going to start with our regular domain of negative infinity to infinity. We're going to go up to 1. We cannot equal it, so we're going to put a parenthesis. We add our union symbol, and then we want all the numbers bigger than 1. And so we get negative infinity, comma 1, both in parentheses, union 1, comma infinity, again, both in parentheses. All right, so even though it's not a rational function, we can still go ahead and compute the domain. All right, the last thing, let's look at one more. Let's come down to C. C is also not a rational function. This one is not a rational function because the denominator is not a polynomial. Okay, we can still find the domain though. And so for our domain, this is going to be the most complicated one that we're going to look at. And this is not going to be a high priority, okay? But just to show you how this works. All right, the first thing that we have is x minus 8 has to be greater than or equal to 0 because, remember, we cannot take the square roots of negatives. This was if it just existed by itself. Now, we do have one more condition. I need to get rid of the bar on the bottom. It cannot equal 0 because the denominator cannot equal 0. And if we combine these two statements together, then what we get is x minus 8 has to be strictly greater than 0. All right, if we go ahead and solve this, we can add 8 to both sides, and we get x is greater than 8. In interval notation, we just have one interval, and that is going to be 8 to positive infinity, and we have parentheses around both. All right, so that takes care of these examples. Okay, and except for like example B and C, especially C, this is not anything new. We have talked about domain of rational functions in previous courses, and we've also talked about it at the beginning of this course. All right, so now let's get into the new material. The main thing that we're going to be adding into our repertoire for this particular course is we are going to be graphing rational functions. And so we're going to start with our domain, and we want to know how is the domain translated visually. Visually, what we are going to have is a vertical asymptote. Okay, a vertical asymptote, what this is going to be is a vertical line that the graph approaches, but it does not touch or cross without lifting our pencil off the paper. So, to find vertical asymptotes, we do the exact same thing that we did when we talked about domain. In order to find the vertical asymptotes, we set the denominator equal to 0 and solve. The difference is, with domain, we say x is not equal to this number. Vertical asymptote is a line, and so we are going to write it as an equation. So for instance, we had on one of them, x is not equal to 1. Well, when we talk about vertical asymptotes, we just say x equals 1, and it's an asymptote. When we graph asymptotes, we are going to use dashed lines. These are our helper lines. We used a dashed line because it is not actually part of the graph. All right, so let's talk about formal definition. And again, I'm not going to put a lot of emphasis on this. The line x equals k is a vertical asymptote of the graph if f of x tends towards positive infinity or f of x tends towards negative infinity as x approaches k from either the left or the right side. Okay, so as we get closer to the value of the asymptote, as we get closer to this asymptote, vertical asymptotes, what we're going to see is our graph is going to go forever up and or forever down. And that's what happens, okay? All right, now, not every rational function will have a vertical asymptote. We do have a special case, and our special case is going to be if you have a factor that appears in the numerator and the denominator. What happens in terms of the function is they cancel out. Now, what this means visually is we are going to graph the simplified function, but we do still have a domain restriction. And in order to identify the restriction on the domain, what we do is we put a hole using an open circle at that particular number. All right, these are our vertical asymptotes. Now, rational functions quite often also have something called a horizontal asymptote. And a horizontal asymptote is a horizontal line that the graph approaches as x approaches positive or negative infinity, as x goes forever to the left or as x goes forever to the right. There are going to be two options for horizontal asymptotes. The first one we have is we're going to look at the degree of the numerator and the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. Our second option, if the degree of the numerator is equal to the degree of the denominator, then we have the line y equals a over b is the horizontal asymptote, where a and b are the leading coefficients of the numerator and denominator, respectively. We do have one more case, and we do not discuss it in this course. You'll see it if you take pre-calculus next semester. And the last option we have is if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If it's exactly one more, we have something called an oblique or a slant asymptote, but this is something that we will look at next semester. All right, so that's going to be the first thing that we're going to talk about, is we're going to focus on rational function, and we want to figure out what are the asymptotes, both horizontal and or vertical. All right, the next thing that we're going to do is we're going to be given some equations, and we want to talk about how we find the horizontal and vertical asymptotes. Okay, let's start with example A. Example A is, first and foremost, it is a rational function. And so because we are going to be doing a bunch of different things on these, I do recommend kind of writing notes to yourself to keep track of what we're finding. All right, vertical asymptote. Remember, vertical asymptote is where is the denominator equal to 0. And so if we set our denominator equal to 0, we solve for x, and we can subtract from both sides. We get x equals -5. We want to make sure that we leave it in equation form. It is an asymptote. Asymptote is a line. It does have to be an equation. All right, for our horizontal asymptote, you can go ahead and compare degrees and all that, and that's fine. But what I like to do is divide the leading terms. Okay, and we're going to have one of two things that happens. The first one we have is, for instance here, if we divide our leading terms, I want to divide just the 3x by x. It is a horizontal line, so I'm going to say y equals. If we divide 3x over x, this does simplify. We can cancel out our x's, and we are left with y equals 3. And that is our horizontal asymptote, y equals 3. All right, let's go ahead and look at a couple more and see what we can do. Let's come over to example B. Our example B, we're going to start with vertical asymptotes again. Okay, we have denominator equals 0. And so if we set the denominator equal to 0, you can either factor or do square root property. We get x squared equals 16. And if we take the square root, we get x equals plus or minus 4. Now, I do want to be very careful because remember that these are lines, not numbers. And so in homework and on paper assignments, we do want to separate them. These are individual lines. And so I'm going to go ahead and separate this into the vertical asymptote is x equals 4, and we have a second one at x equals negative 4. All right, for my horizontal asymptotes, we want to divide the leading terms. All right, if we do this, we get y equals 3 over x squared. And all I want to do is look to see if we can simplify this. And this does not simplify. The main thing when we talk about asymptotes is remember that horizontal asymptotes is we want to know what does this become as x gets really, 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 really big. Okay, so let's just kind of think it through. All right, if x is 1, we get 3. If x is 10, this becomes 3 over 100. If x is 100, this becomes 3 over 10,000. And if you notice, this gets smaller and smaller and smaller and smaller and smaller. And what it's happening is it's getting closer and closer to 0. So the main thing is, if you have a denominator that does not cancel out, then you have a horizontal asymptote of y equals 0. Now, one thing to note about this is you can have multiple vertical asymptotes. You will only ever have one horizontal asymptote. All right, let's look at a couple more. All right, let's come to example C. All right, example C, the first thing that I want to do is I'm going to go ahead and factor this out. There's nothing wrong with that, okay? And here's the thing, if we factor this, on the bottom, what we're going to get is 2x and x. I have 5 and 1 multiplies to 5. And we do have different signs because it is a minus 5. That means I do need a positive and a negative. I want my larger quantity to be negative, which is going to be my insides. All right, if we factor the numerator, this is a perfect square trinomial. And what we get is x plus 1 times x plus 1. Okay, we were only asked to find asymptotes, and that's what we're going to go ahead and do. So the first thing that we have is right here, my x plus 1's cancel. And so technically, when we graph this, it is the same shape as x plus 1 over 2x minus 5. All right, so we just have one vertical asymptote here. If we set that 2x minus 5 equals 0 and solve, 5, and we get x equals 5 halves. That is a vertical asymptote. All right, the second thing that we have is we do have a horizontal asymptote. And so remember, horizontal asymptotes, what we're going to do is we are going to divide the leading terms. And so if we do this, we get y equals x over 2x. My x's cancel, and I am left with y equals 1/2. And so we do have a horizontal asymptote. Now, even though it didn't ask for it here, I do want to talk about, okay, well, what does that other thing do that we crossed out? Because it is part of the domain. X cannot equal -1. If you plug in -1 to the original function, you get a denominator of 0, and it's undefined. And so what happens here is we have a whole at x equals -1. Okay, so a hole is a point. It's a ghost point. And so in order to find this ghost point, what we do is we're going to take this -1 and we're going to plug it into the simplified function. And so if we plug this into the simplified function, what we get is -1 minus plus 1 over 2 times -1 minus 5. And we get 0 over -7. And so when we get to the graph, what we're going to have is a open circle at -1, 0, but everything else around it is going to be based on the simplified function. All right, the next thing we want to look at is example D. All right, if we look at example D, what we have here is we have our vertical asymptotes. We set the denominator equal to 0. And we get x equals -2. We leave it as an equation and we're done. All right, the next thing I want to know is, do we have any horizontal asymptotes? And so horizontal asymptotes, we are going to go ahead and divide the leading terms. And if we do this, we get y equals 4x cubed over x. And if you simplify this, what you get is 4x squared. This is not a horizontal line, okay? And so we have no horizontal asymptote. And that is all we're going to say about this particular example, is no horizontal asymptote. If you get that, that you don't have those leading terms simplified down to a single number, or you don't have variables that are still running around in the denominator, then you have no horizontal asymptote. All right, that takes care of these examples. All right, the next thing that we're going to do is we are going to go ahead and look at some equations, and these are going to be very general equations. And we want to match each equation with its graph without using a calculator. So far, we only have two things in our system, or in our bag of tools, which is asymptotes. And so that's what we want to do, is we want to go ahead and figure out what are the asymptotes going to be for each one of these. All right, let's start with example A. Example A, we have f of x equals a number divided by x minus 1. All right, if we talk about the vertical asymptotes, remember we set the denominator equal to 0, and we get x equals 1. All right, for my horizontal asymptote, we want to divide the leading terms. And if we do that, we get a over x. As x gets really big, this fraction gets really small. And so because we do still have that variable in the denominator that does not go away, we have a horizontal asymptote of 0. All right, so those are my two asymptotes. Okay, so let's go ahead and come down to our graphs and see which one of these is going to be our option. Okay, for this one, we have x equals 1. Remember, this is a vertical asymptote. And so for our vertical asymptote of 1, we have we have our first graph, top left graph, and we have our top right graph. Now, we have a horizontal asymptote of y equals 0, and that's the x-axis. And so the top right, this is going to be the graph of example A. All right, let's come to example B. We're going to do the same thing. We want to start by identifying horizontal and vertical asymptotes. All right, so vertical asymptote. Remember, this is denominator equals 0. If we set our denominator equal to 0 and solve for x, we get x equals 1. All right, for our horizontal asymptote, we want to divide the leading terms. And so if we do this, we get y equals 2x over x. My x's cancel, and I have a horizontal asymptote of y equals 2. All right, so let's see which graph is this going to be. All right, for this one, this is going to be the top left graph. We have a vertical asymptote still of x equals 1. We have a horizontal asymptote at 2, which is this horizontal line right here. And so this is going to be example B. All right, let's go to example C now. Example C, we have h of x equals x minus a over x plus 2. All right, so vertical asymptote. Is where the denominator equals 0. If we set the denominator equal to 0 and solve, we get x equals -2. All right, for horizontal, we want to divide the leading terms. And if we divide the leading terms, we get y equals x over x, and that simplifies down to y equals 1. All right, so let's go ahead and see what we have down here. Okay, we said a vertical asymptote of -2 and a horizontal asymptote of 1. And so that is going to be the bottom right graph. We have our vertical asymptote of -2. We have our horizontal asymptote of 1. And then the rest of it is our graph. All right, last one. We have example D. Okay, example D. The first thing that we have is when we talk about our vertical asymptotes. And I know it's kind of weird because we don't have a number there, but what we do is we set our denominator equal to 0. And I'm going to go ahead and do square root property. We move our a to the other side. We take our square root, and we get plus or minus the square root of a. Okay, and the important thing here is we have 2. Okay. All right, the other thing that we want is the horizontal asymptote. All right, we're going to divide the leading terms. And if we do this, we get y equals -2x over x squared. And I can cancel 1x. This simplifies down to -2 over x. But I do still have a variable running around in the denominator. And so as x gets really big, this gets really small. And so we have a horizontal asymptote of y equals 0. And we don't care that we have a negative on the top. It doesn't matter. It still gets really close to 0. All right, so when we look at this one, the only thing that we have that satisfies this is the bottom left. This is the only one that has 2 vertical asymptotes. And if you notice, we do have that our graph, as we get larger, as we go towards infinity and negative infinity, we are getting closer and closer to the x-axis. All right, that takes care of this half of the material. In the next section, we're going to be not only finding the asymptotes, but we are actually going to create the graphs ourselves. So go ahead, take a break, and then we'll come back and look at that.